All right, biology applications of logarithms and exponentials. In the previous video, we talked about compounding interest and how that worked, and we saw a formula that was exactly this formula, but it was used for continuously compounding interest. The same formula works with 1.5 million different things, one of which is continuous growth / decay of biology systems, of bacteria growing in a petri dish. It's called uninhibited growth, and I am not a biologist, so I'm not going to sit here and lecture on that. It's obviously a theoretical model, and uninhibited growth is not something that really exists. That would mean that a population could grow without anything hampering it forever. There's always going to be resource limitations, blah, 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 blah. This is theoretical. We're just having fun here, right? We're just doing some mathy stuff. So here's how this formula works in relation to biology, in particular in populations. The A is still like the total amount, right? A is always the total amount. In the case of population, that would be the total population. This is still the accumulated amount. And as it relates to population, it is the population after T years, or population after T time, after time T. The P is still principal, but it's different. Instead of it being the initial amount you invest, it's the initial population. T is still time. It sometimes is in years, it sometimes is in hours, it sometimes is in minutes. It all depends. So it's not always in years like it is with finance. And then the R is a little bit special. So the R is what we call the relative growth / decay rate. Relative growth / decay rate. If your population is growing, then this number will be positive. So growth means this number is positive. And if your population is decaying, or if you're talking about radioactive decay, as we will in the next section, your R is negative. Okay. So let's go ahead and do some examples. The number A of bacteria present in a culture at time T in hours obeys the law of continuous growth with this right here formula. This function, A of T is equal to 1,000 e to the 0.01 T. Determine the number of bacteria at T equals 0 hours. T equals 0 hours is going to be the initial population. Now, sure, you could plug in 0 to this formula. You could, and if you do, you'll get the same answer I'm about to give you, but we know that the initial population should be this number outside of the E, right? This is the R, this is the T, this is the P, right? P is equal to 1,000. This is the initial population. So how many bacteria were there at T equals 0 hours? There were 1,000 bacteria. What is the population after 4 hours? Round to the nearest whole number. This is a function right here, so this is function notation. I'm going to plug in 4 for T. T is equal to 4. So I have A of 4 equal to 1,000 e raised to the 0.01 times 4. And if you plug that bad boy into your calculator, you should get the number 1040.810774, which is not rounded to the nearest whole number. We don't take a half bacteria ever. We don't count populations that way. So if we round this, this is 1,041 bacteria after 4 hours. So there's 41 more bacteria after 4 hours. When will the number of bacteria reach 1,700? Round to the nearest hundredth. Okay. When will it reach 1,700? That's the amount we want to accumulate. We want to accumulate 1,700 bacteria. Okay. We have our formula right here. A equals 1,000 e raised to the 0.01 t. If A is 1,700, 1,700, and we want to solve for t, we're going to need to get the e by itself and then apply the natural log. So to get e by itself, it always ends up being this kind of same game we play each time. Divide both sides by 1,000. 1,700 divided by 1,000 is going to be 1.7. E raised to the 0.01 t. We're trying to solve for t. We're going to take natural log on both sides. So this is natural log of 1.7 is equal to the natural log of e raised to the 0.01 t. Remember, ln e cancels itself out. The rule is ln of e raised to the whatever is equal to the whatever. So we have ln of 1.7 is equal to 0.01 t. Solving for t, dividing by 0.01 on both sides. Boom, boom. We get t is equal to ln of 1.7 all divided by 0.01. If you plug this into your calculator and round that number to the nearest hundredth, you're going to get 53.06, and then our units are hours. So it'll take 53.06 hours. Come on, make a square, make a rectangle. There you go. For our population of bacteria to reach 1,700. Fun. All right. Here's another one. The area covered by a certain population of bacteria increases according to a continuous exponential growth model. Suppose that a sample culture has an initial area of 43.2 millimeters squared and an observed doubling time of 9 hours. Let t be the time in hours passed, and let a be the area of the sample at time t. Write a formula relating a to t. Leave r as an exact value. Now, my friends, let me come back to our compound interest, because at the very end of this compound interest section, we talked about these doubling time formulas, and I said they would come in handy in other ways, and I was not lying, because they are now handy. All right, these two formulas, they're the same formula rearranged. They relate doubling time to the interest rate. And that was the interest rate of an account, right? But it also, if we're not talking about accounting, would relate the relative growth rate to the doubling time. So this works with population. All right, this is important because we have a doubling time right here, right? Observed doubling time of 9 hours. Doubling time equals 9 hours. 9. Maybe I'll write the word doubling time. Doubling time equals 9. So if the doubling time is 9 hours, and we're trying to find a formula relating a to t, really what that's saying is we want this formula. We want our PERT. We're trying to find PERT here. And t is going to be unsolved for, as is a. We're looking to find p and r to plug into this formula, because then I'll have a formula. So essentially, it's going to end up looking like in function notation, a of t is equal to, we need to find this number, e raised to the, we need to find r, and then t. So we're looking to fill in this and this, p and r. R, no big deal. We can use this formula right here, right? R is equal to, doubling time is on the bottom, but I want to center it, so I'll write it first. Boom. ln2 over doubling time. We know what the doubling time is. The doubling time is 9 hours. So this is ln2 over 9. ln2 divided by 9. I was about to just round this number, but it says leave r as an exact value, so we are leaving r as an exact value. So we're going to come back for you. Here, this is our r. P is what we need now. P is the initial population. In this problem, it's not population, but area, but the same idea, right? Initial area, initial whatever. P is 43.2. So we have P, we have R, we have everything we need to fill in this formula to relate the area at time t to the variable t. So it looks like this. A of t is equal to, P is 43.2, E raised to the, our interest rate, our relative growth rate is ln2 divided by 9 times t. Boom. There she is. What will the area of the sample be in 7 hours? Do not round any intermediate computations. Round your answer to the nearest 10. What is it going to be when time is 7? Well, we have a formula, right? Take out the t, replace it with a 7. And plug it into your calculator. If you plug it into your calculator and you do everything correct, and I do suggest trying because sometimes we don't know how to use our calculators as well as we think we do. And it's not to say that that has nothing to do with intelligence or anything. It's just sometimes when we enter something, it doesn't look like we think it's supposed to look, and then we get the wrong answer. So just be sure that you're entering it and getting the same answer as me. If you enter it and round to the nearest 10th, you should get 74.1, and that's millimeters square millimeters. Bam. So this is legitimately just plugging 7 into the formula we got up here. And that's it. That's the end of that problem. All right. We're going to do one more example. It has 2 parts, but one more example on biology, and then we're going to talk about radioactive decay and another chemistry application in the next section. And then we're done. And then we're done. All right. The number of bacteria in a culture decreases according to a continuous exponential decay model. All right. What does that mean? It means our R value is going to be negative. R value is going to be negative because it's decay. The number of bacteria in a culture decreases according to a continuous exponential decay model. The initial population in a study is 500 bacteria. Initial population is 500 bacteria, so P is 500. And there are 390 bacteria left after 9 minutes. All right. Don't put in T equals 9 yet. Hold on for a sec. So there are 390 bacteria left after 9 minutes. We're trying to find the relative decay rate for this. Oh, okay. I'm saying it this way because the way that this question was initially phrased, if you're looking for this question on Alex, this question doesn't ask this first part. This question just goes blah, 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 how many bacteria are there after 14 minutes? And you have to be careful because you get two time numbers when it's asked that way. You get a 9-minute number and a 14-minute number. Now, when I separate it like this, you don't see it that way. But just kind of be aware. I don't know what I'm saying, but I'm not starting this video over. In problems where you're given two times, you're told like this happened after so many minutes, and how much is the population after this amount of time. Typically, you're using that first amount to solve for a preliminary number that you don't have. In this case, it's going to be the relative decay rate, and then using that relative decay rate in the formula to then plug in our new time. Anyway, our relative decay rate, we have 500 bacteria, we accumulate 390 bacteria after 9 minutes. So the accumulated bacteria is 390, and that happens after 9 minutes. T is equal to 9. So we're pert, or we're, A is equal to pert. So A is 390 equal to 500. E to the, we don't know what R is, we're trying to figure that out. RT, so 9 is T. We have 390 equal to 500 e to the 9r. We have to get e by itself, and then we'll apply natural log to both sides. So divide both sides by 500. 390 divided by 500 is going to be 0.78. 0.78 equal to, and then these cancel, e raised to the 9r. Applying natural log to both sides, ln of 0.78 is equal to ln of e raised to the 9r. The ln e cancels. Remember, ln of e raised to the whatever is the whatever. So we have ln of 0.78 is equal to just the exponent 9r. To solve for r, we are dividing both sides by 9. Boom, boom. So we get that our relative growth rate, or decay rate rather, is ln of 0.78 divided by 9. And you might be looking at that number and saying, uh-oh, that number is positive and we were supposed to get a negative number. But let's plug it in to our calculator and let's round it to the nearest 10th. We're rounding the percentage, by the way, to the nearest 10th, not the decimal number. So I get negative 0.0276. That's enough decimals for me. Moving the decimal place over 2 times, we get negative 2.76% is the relative decay rate. Now, you could argue that this should be like positive because the word decay means negative. So saying negative decay would be counterintuitive, but I don't know. We all know what I'm trying to say here, right? It's negative 2.76%. It decays at a rate of 2.76%. That's the relative decay rate. That's also enough for us to then fill in our formula and figure out how many bacteria there are after 14 minutes. So our formula, A equals P e to the RT. The initial amount is still the same. There are still 500 bacteria initially. It's 500 bacteria initially. The R value is right here, right? This is it as a percentage, but we're not looking for the percentage. We're looking for the decimal when we use the formula. So this is negative 0.0276, and then T. In our case, we want to know after 14 minutes. So T is equal to 14. How many are there? All right, so I plug this into my calculator as I do with everything. And I get 339.7. We're rounding to the nearest whole number because we don't take partial bacteria. So this is 340 bacteria after 14 minutes. We should ask ourselves, like, does this number make sense? So we started with 500 bacteria. It's decaying, so it makes sense that this number went down. Let's see, after 9 minutes, there were 390 bacteria left. After 14, there was 340. That makes sense. After more time has passed, there are less bacteria. I like to do tests like that to just make sure that logically everything checks out. It's a small thing you can do to catch yourself from making an error. Anyways, those are some examples of biology applications. The next video is going to go over chemistry applications. I'll see you in that one. Bye.